and those results saying what's happening when we sort of step around in this weight space. Okay, so what we have done is that the states are organized in some hexagonal pattern like this. And acting with the step operators, we walk around here. So this would be acting with T. This would be acting with U, and this would be acting with V. So we have the analog of the SU2 case where we could walk around between the spin Z eigenvalues, but now we have this in a plane instead of just one direction. I will now be quite sloppy in my description of what's happening in this plane, and the reason is that I don't think it deserves quite as much attention as it receives in these lecture notes. I think we simply have even more interesting things to do. But analogous to the SU2 case, we define maximal or highest weight state. So in the SU2 case, that was the state with the highest LZ. Well, here we have 3 directions and we cannot maximize them all. So actually we define the highest weight state to have the property that if we act on T with T on it, we get 0. If we act on U minus with it, we get 0. And if we act with V plus on it, we also get 0. So it's the state mostly in that direction. But one could have had other definitions. One can prove, and 2 years ago we actually did that, but I don't think we will do it this time because I think simply we have even more interesting things to do. But one can prove that in the weight diagram, so this is the pattern that we will have in a 2-dimensional plane, so where the states are organized in eigenvalues to these operators here, that has no concave angle, but it has convex angles like here. So I will, however, try to convey the broad picture of what is happening in a few words of why at some section of the weight diagram having no concave but convex angles. And let's take a look at the states here, going then along the U line. So for convenience, I have drawn the directions here. We have the T direction, the V direction, and the U direction. So now if we take a look at the states here between what's called M and N in this diagram. So now we are walking along the V axis here. We see that this V represents an SU2 space. So these states here, they're also in some SU2 representation. So they must obey what we expect from that. And this means that this line here is symmetric when we mirror across its middle. And the same thing actually applies for this multiplet here and for this multiplet here. So along these V lines, we have what we call V multiplets. And since they are also SU2 multiplets, they must fulfill what we expect from them, and that means that this state must have a corresponding state here, this state must have a corresponding state here, and this state must have a corresponding state here. So it implies that this length here must be the same as this length here, because all these states have a mirrored state here when we mirror in this axis here. So we have a symmetry with respect to mirroring in this axis. So from this, we conclude that the length of the multiplet here should be the same as the length of the multiplet here. We can also similarly take a look at the states along other lines, and we should be able to make the same conclusion. So, for example, then, since this is all symmetric, we should have as many states. We should have a symmetry also when mirroring along this line. Sorry, this was the line we discussed, but we should have a symmetry when we mirror along this line and the symmetry when we mirror along this line. So the multiplet should be symmetric with respect to mirroring here, here, and here. And this means that it has a hexagonal pattern with 2 degrees of freedom. So one is the length here, and the other one is the length here. Given those lengths, the full multiplet follows. So if we have length p here, then we have p plus 1 states here. We have p spaces here and one more state. And similarly, if we have length q here, we have q plus 1 states here. So we can relate the shape of the multiplet with the states, number of states along these directions here. So we have then, for example, the p plus 1 states here is 2 times some jv. So the v eigen, the j in the v direction plus 1. So from this we can find the jv. So that would correspond to the total spin along the v direction, and it is then p over 2. The point is then that the multiplet can be fully characterized by these numbers, by the p and the q. And this is where I will start jumping over a lot of stuff. So I just want to say roughly how this works, because that's nice to know, and it's nice to know that it exists, but I will not spend so much time on the details. But what one will find is that, and we will actually to some extent motivate why, is that the states in this hexagonal multiplets will sometimes be doubly occupied. And in fact, we have the property that the outer shell is singly occupied. The next shell is doubly occupied unless the previous shell was triangular. Here it's hexagonal, so the next shell, that is this shell, should be doubly occupied. And then when we move in, we will have, since we move in now from another hexagonal state, we increase the number of states in a certain position by 1 more. So we will have triply occupied states here. And this is not super hard to derive, but it's also not trivial to derive. And I simply don't think it's worth the time. But you should know that there is something like this, and this is roughly how it works, and you can go and check the details if you would ever need them. Okay. So I want to say a few words about the most famous multiplets in this weight diagram. So first of all, we have, of course, the singlet representation. So the singlet representation has an eigenvalue 0 along all directions, so it's in the middle here. Then we have the triplet representation, and we can then describe it as if the quarks are in these states, and we draw it like this. The anti-triplet representation would correspond to turning this triangle upside down. Then, if we combine the triplet and the anti-triplet, we can get among other things, the octet state. And the octet state would correspond to gluons then. So this would be a gluon, this would be a quark, and this would be an antiquark. And then we can have higher representations corresponding to those. We have no direct product, but we can, no particle, but we can have, for example, two quarks being in an overall sextet representation, etc. And when we combine representations, we do it much like we did it for the quarks, for the SU2. So what we do then is that we start with some multiplets. So for example, we start with the triplet multiplets, and now I'm drawing black dots on black background, so it's not visible, but I want to copy it over here. So this is my the triplet representation. Then what we did in the SU2 case was that we overlaid the multiplet centered around each points in the other SU2 multiplet. We will do the same here. We have two directions, so we have two directions to center. But I should then draw centered around each of these 3 points, say these points here, if I'm considering the product between a triplet and an anti-triplet. So let me do my best to do this. So I now want to take this guy here and draw it 3 times on top of that guy here. So let's see how that goes. Okay, so I then, let's say I start here, then I have one state here, I have one state here, and I have one state here. That's the 3 states that I can get to from that one. Then I start in this state, and I have one state here, so now I will write like it. I'm sorry. What I'm doing is overlaying the same multiplet on itself. Actually, that was not what I intended to. Yes, so the mistake is here. So I wanted to take, so what I've drawn here is the triplet. And now I wanted to take the anti-triplet, this guy here. Yeah. Okay, so then my first state should be right on top of this state here. And I should try to make it to scale, so it takes a little bit of exercise. So I will have one state here, so this comes from this state there. And I will have one state here coming from there, and I will have one state from this guy, so it will end up here. And similarly, I should start from this state. I should draw one state here. I should draw one state down there and one state down there. And I should start from this state. I should draw one state up, one state down right, and one state down left. So now I have 3 states in the middle, and I have a hexagon. The 3 states so I can now try to decompose this into known multiplets. And if you recognize the outermost shell, it looks a lot like the octet shell here. And indeed, this is also what it is. So from this we get this. This is now intended to be a regular hexagon. And of the states in the middle, we should take 2. So we should have 2 states there. So this is our octet representation. Now we have taken almost all dots in the representation, but we have one little dot remaining. And this is our singlet representation. So what we have derived is that we have found then the octet representation and the singlet representation when we take 3 times 3 bar. And one can do the same game with more complicated multiplets. Actually, there is a more efficient way of deriving this, which is based on symmetries and Young diagrams. So let's see how much time we will have to speak about that. Are there any questions to this? If not, I like to move on to the Lorentz group. If you were not persuaded by my admittedly less than perfect drawings, you think there is a better drawing somewhere here. Here it is. Here we take instead 3 times 3, and we do the same game. We place one of them on top of the other, and we get a few states. Okay. Then I like to swap document, because I like to have the most updated document from this morning. And I will move on to the Lorentz group. So we will talk about space and time, or perhaps rather space time. So we will talk about the Lorentz group. And we can define the Lorentz group as the set of all transformations that preserves the inner product of Minkowski space. So you should know from special relativity that this quantity is conserved or expressed in terms of the metric like this, or expressed as x0 squared minus x1 squared minus x2 squared minus x3 squared. So this eta here is the metric, so it's diagonal 1 minus 1 minus 1 minus 1 in the particle physicist convention. If you have not studied particle physics but only gravity, you have most likely seen it with the opposite signs everywhere. Both conventions are common, but in different fields. But now we take this definition, and if we look at it, we see that we should leave the metric invariant. We see that this is actually nothing but the definition of the group O1, 3. So the metric eta was called E before, and it had a certain number of minuses and a certain number of pluses. And we define the group such that we should fulfill such a relation. So this means we can now sort our Lorentz group into one of the groups that we have encountered before. Maybe I should say as well that if you have not come so far in your studies, maybe you think that the Lorentz group is just all the boosts. We will shortly see that that doesn't work. The boosts do not form a group. You need rotations as well. And if you include boost and rotations, you get SO 3,1. Here we have 1,3. So we are actually here also including mirroring, because clearly mirroring does not change this metric, and time reversal as well. Okay. So now, starting from this actually as a starting point, we will probably take another route to the Lorentz transformations compared to what you have seen. So we will derive the Lorentz transformations from the group properties and see what we get. Okay, so from the definition from up here, we see that we can take the determinant of both sides, and we have an equal sign here. The determinants must obviously be equal. And then we use the determinant of A times B is determinant A times determinant of B. So we have here determinant lambda transpose, but that is determinant lambda, determinant eta, determinant lambda, and this should be equal to the determinant of eta. Well, clearly we can then cross out the determinants of eta, and what remains is the determinant of lambda squared should be 1. So the determinant of lambda should be plus minus 1. This is something that we derive. Now, if we take a look at the 0, 0 of this matrix, so here we have eta 0, 0, so this is 1. Then we get a constraint on the components of lambda. So we here take this and we write it in component form. So we take component 0, 0 of this matrix. So 0, summation index 0. And now if we recall the form of eta, we recall that we have a 1 for the 0, 0 component. So then we have lambda 0, 0, lambda 0, 0. So we have lambda 0, 0 squared. And for spatial components, we then have a minus sign, and then we have lambda 0I squared should then be so all of this should be eta 0, 0, so it should be 1. So we must then, so what we are looking for is then the set of transformations fulfilling this. So not probably the starting point from special relativity. Okay. And now we see here that in order to fulfill this, lambda 0, 0 squared must be larger than or equal to 1. So that means that lambda 0, 0 must either be larger than or equal to 1, or it must be smaller than or equal to minus 1. What we will do now is that we will divide in the Lorentz group in 4 so-called components according to the sign of this guy, and according to the sign of this guy. So the determinant could be plus minus 1, and this guy can be smaller than or larger than 1. Or larger than 1 and smaller than minus 1. Okay, so we define then, and we draw it with an upper arrow, the orthochronous, so preserves the direction of time component of the Lorentz group. So that will be one way of characterizing it, and the other one will be determinant is plus and minus 1. And that plus and minus 1 is then denoting the determinant, so if the group is proper or not so-called proper. And often we actually talk about the restricted Lorentz group. So we will actually mostly be talking about the restricted Lorentz group, which has determinant 1 and lambda 0, 0 being also 1. So this is what we'll mostly talk about, but you should be aware that there are other so-called components of the Lorentz group, in total 2 times 2 components. And I should say that these 4 components are disconnected in the sense that you cannot take a Lorentz transformation to move between them. So I should be more precise. You cannot take the Lorentz transformation in one of the components to move to the other components. You have to involve parity and time reversal, which are also part of the Lorentz group actually. So that is part of O 1,3, but it's not part of SO 1,3. Okay. Now, parity then is swapping the direction of all space components. So it looks like this. Time reversal is swapping the direction of t. So we have this. And as mentioned, we will mainly be interested in the component with determinant 0 and in which the direction of time is also preserved. Do we have any questions so far? Okay, then we will have a look at the algebraic structure and the generators of this group. So we will now try to explore what matrices we can have and how they can be generated. So what we are trying to do is that we try to find the Lorentz group, which is acting on 4 vectors in Minkowski space, and it's given by V, 4x4 matrices. From that, we would assume that we have 16 parameters, but we have seen in an exercise, although it was for 04, I guess, that we have fewer parameters, and counting the number of parameters, one can see that we actually only have 6 continuous parameters. So in general, n times n minus 1 over 2 for generic or orthogonal groups. So then we want to find the generators. And let's not start from scratch. Let's use what we know from before, namely how to generate rotations in 3 dimensions. So for rotations in 3 dimensions, we had that R transpose should be 1, and now I just inserted the -1 from the -1 that I had on the diagonal of the 4x4 matrix. Of course, it can be crossed out everywhere. And we then use old knowledge, and we find that all the rotations, the Lorentz transformations of the rotations, are given by a 1 in the time component, so nothing is happening to time, and then the spatial components are mixed. So we have a 3x3 matrix describing what's going on there, and this is the ordinary rotation matrix. Good. So we don't have to rederive anything. We just copy what we know from before. We can generate a rotation around an x-axis, around a y-axis, or around the z-axis. This is then assuming that we use actually the mathematician's choice. So we had E to generate just directly without an additional I. And in this case, the generators are non-Hermitian, as you can see, anti-Hermitian. Later on, we will use the physicist's choice. So we will form linear combinations with an I instead, and compensate for that with E2 minus I, so it will be the same thing, same group that's generated. But since this is a real group, in the sense that it has real matrix elements, it makes sense to start with the mathematician's convention, so we don't have to carry around that additional factors of I anywhere. Okay. So we want to then find the group elements that are generated like this, E2 linear combination of generators. The rotations we hadn't found, and now we are looking for the boost as well. So what we do then is that we take the defining relation for the group, and we expand it to first order in alpha here. So we have then from this we have 1 plus alpha AKI, and then we have the eta, and then we have 1 plus alpha B, another summation index KB transpose, and that should be equal to eta. So that was the defining relation. Now, of course, the ones here, the 1 times 1, that gives us the eta already. So the other terms should cancel. And considering terms to order alpha, we have multiplying order alpha terms, we have Ka eta here. And here we have also eta KB, or for component AKA. So we have this constraint here with the transpose from up here and the minus sign because it's moved to the other side. So this we must then satisfy. So now we are looking for those transformations, and we then want to consider a boost in along the x-axis. So actually we steal here all knowledge that this should be the boost that is not changing z and y. So we steal here that we should place our zeros here. But the only thing that gives us is the option to call it a boost in the knowledge that it makes sense to call it a boost in the x direction. It doesn't give us any more degrees of freedom or makes the derivation less general. Okay, so now what we do then is that we assume that we only want to change this block here. That makes it a lot easier because then we can forget about this rest of the matrix and just consider this 2 by 2 block. And then we take again the defining relation. So we had defining. So the defining relation was here, lambda t eta lambda is eta. So we had then lambda t eta no, this looks strange. We should have it doesn't matter, but I think we should have, it makes more sense to have the transpose here because this is how we are normally transforming a matrix here, and this is what we have here. We take that constraint and then we are multiplying by lambda inverse. No. So we are multiplying by one matrix on one side of this equation to obtain this thing here. So we want to get rid of the okay, so let's see. So this is our lambda essentially. This is our eta. This is our and this is our lambda transpose. So we should have multiplied. We have multiplied with lambda from actually we need the other version actually. So we need to move the t here. T and now look, it's very easy. It's just sometimes a bit hard when you have a lot of people staring at it, but it's basically just this equation. And I'm sure you can sort it out faster than I can with this many people staring at me. You have to fix, yeah.
Malin, isn't it just the equation from above, which is Ka eta equal to negative eta K transpose?
Right, it is, and this is what I was trying. I guess you're right. This is what I was trying to rederive because I didn't remember that it was standing there. So it is. That is what it is. So yeah, exactly. So this is the K alpha, and this is this guy. It goes there. This is the eta. It is this guy. It goes there. And this is the minus sign from there. And this is the eta from here, and this is the K alpha T Ka. So this is the transpose standing here. Let's double check that it is indeed a transpose. So the A and the D, they keep their position. The B goes down there and the C goes there. Thanks. Good. So now, so this is was the way to see this equation. Okay, from this we now want to identify the components. So if we simply make this matrix multiplication, so we have on this side we have A from this line times this line, we have minus B from this line times that line, we have C from that line times this line, and we should have minus D from this line times this line, correct me if I'm wrong. Then this should be equal to what we get from this side. So we have then first minus A minus A minus C B, because we have two minus signs, and D. So now let's see if we have the same constraints as in here. Yes. So first we conclude then that A is minus A, and this is this constraint. Then we conclude that minus B is minus C, and that is that constraint. Then we conclude that again that C and B are equal, and we conclude that minus C and D are equal. So in other words, since minus D is D must be 0, and since minus A is A must be 0, and B and C must be equal. So we then take, so we are then actually left here for this for the matrix that's only affecting this 2 by 2 block. We are then left with only one degree of freedom, and that degree of freedom must be such that the letters A and D are equal. So we have this. Sorry for the confusion. The confusion came about because I had forgotten that it was done at the algebra level. So I tried to get it to work at the group level, and it didn't quite work at the group level. But it came from this constraint here that we had derived. Okay, so in this way we have this for our boost in the x direction, and of course it's exactly the same game to see that we have this for the boost in the y direction and this for the boost in the z direction, and this completes the finding of the generators of the Lorentz group. So we now know how to boost, and we know how to rotate, at least at the generator level. Now let's have a look at the group level, and let's consider this interesting 2 by 2 block. So we should exponentiate this matrix e to some parameter, boost parameter, we call it eta, and the matrix that we just found. That is actually pretty easy to do. So we expand the exponent as a sum over 1 over n factorial, and then the argument to the power n. Now, what is nice about the argument is that when you square this matrix, you get an identity matrix. So all even powers here will give us back the identity matrix, including the power 0. So therefore, this sum here, that is the exponent, can be divided into one term over even powers. So we sum here n goes from 0 to identity, but we take only the even powers. So we have eta to 2n over 2n factorial, and then we have the identity matrix. Of course, then the odd powers will just give us the matrix back. So this is the matrix that we have, and then we have it to odd powers, and 1 over 2n plus 1 factorial, and eta to 2n plus 1 factorial. Now, some of you may recognize this as a Taylor series of an expansion of a certain well-known function. I think you would have been more likely to recognize this with alternating signs as well, because then we would have cosine and sine. But this is nothing but the hyperbolic cosine, and this is nothing but the hyperbolic sine. So we have hyperbolic times the identity and hyperbolic sine times this matrix. So we can write it in a very neat form, which I think now you should recognize. So here we get back the boost in the x direction. And taking and moving this block to a full ones for the other, putting together these. My questions, and then I'll also take a break, and then I'll come back a few minutes before we start. If there are no questions, I'll also take a break. So I'm around if you have questions. So it's now 1:15, so let's start again. Thanks. Those turning the camera on. So we were about to derive representation of the Lorentz group, the standard 4-vector representation that you're familiar with. We had just about seen that we can write the boosts as this in terms of what is the rapidity eta that I hope you know from some physics course. If not, I just tell you. And those combined with the rotations give us the restricted Lorentz group. But now we should explore the consequences of the rest of the Lorentz group and the discrete part of the Lorentz group. So we should look at the action of parity and time reversal. And to explore the action of parity and time reversal, we explore the action of parity and time reversal on the generators. So if we first take a look at the action of parity on the rotation generators. Now, parity is of course only changing the direction of space, and the rotation generators, they sit in that 3 by 3 corner of the matrix. But we get one change here, we get one sign there, and we get one sign there. So the effect of this guy is canceling the effect of this guy. So under parity, Li goes to Li. Similarly, it is easy to see that on the time reversal, the time reversal operation sits as -1, and then we have a few ones, and that -1 is not even touching the 3 by 3 block where something is happening here. So L is also invariant under time reversal. So the rotation generators L, they go to themselves, both under parity and under time reversal. For the boost generators, I'm not going to do it, but it is easy to follow through and see where the signs end up. And one can see that under parity, a boost generator will go to minus itself. And similarly, under time reversal, a boost generator will go to minus itself. It will be because just one minus sign is picked up. So you can easily do that, check yourself. So to conclude, the Poincare orthochronous Lorentz transformations can be written in this form, either with no I in the generators, so the mathematician's convention, or with minus I, and this is actually what we will build on for the other representations. Theta dot L, where this is now Hermitian, or theta dot K, where K is anti-Hermitian. So K prime here, I should say. So K, recall that the K generators had this form and zeros everywhere else, for example, for the boost in the x direction. So multiplying this with I will have an anti-Hermitian matrix, and that is quite important to note because that means that the transformation that is generated will not be Hermitian. So, sorry, will not be unitary. The generator is not Hermitian, implying that the group operation is not unitary. So these here will generate unitary rotations, and these here, the boosts, will not generate unitary transformations. Then we also want to explore the commutator of the generators, because this tells us a lot about the group. And some of these commutators you are well familiar with. It's the commutators of the rotation generators. We have seen before that Li commuted with Lj is I epsilon Ijk Lk. Actually, and this is important to note, if we commute the boost generators with each other, you can find this by straightforward matrix multiplication. You get a generator of rotation of the direction around the direction k that is not involved here. So boost generators do not close. And then we can also consider the commutator between a rotation and a boost, and it gives us a boost in the remaining direction. So this algebra is closing, but these do not close. So in particular, these do not close. So we can have a group of only rotations, but we cannot have a group of only boosts. The interesting thing is, however, that we can actually find two sets of commuting operators. We can actually combine generators in these linear combinations. N plus minus is Li plus minus Ik prime, and over a factor of 2. Now, taking these linear combinations, we actually obtain two algebras that close. So the M pluses close in the sense that commuting to M pluses, we only have another M plus. The N minuses are also closing. So if we commute to N minuses, we get another N minus. And the N other is the remaining one. So if we have I and J here, we have the remaining K there. And similarly for the pluses, I, J, and K. However, N plus and N minus commute. So this means actually that we can divide the group into smaller representations. And those of you that have taken the particle physics course, you have actually already seen them as the left and right chiral part of the Dirac spinors that solves the Dirac equation. From a more mathematical perspective, this is also good news because it implies that we can, since we know these guys, we know the SU2 structure very well. The SU2 is sort of the most important group in this course. We build everything else from it. Knowing that and knowing all the representations of SU2, we can construct all the reducible representations of these algebras. And from those, we can find representations of the Lorentz group. Note, however, though, that although the two copies of SU2 are unitary, when we form linear combinations of the generators, we do no longer preserve this unitarity. And in particular, it is generators of boosts that break unitarity. So actually, the states that we have, and that you know it is position, for example, and momenta, but that is not physical particles. That is not particle states because the transformation is not unitary. Then we can connect this. We go back to the SL2C. So if we take E to I Hermitian matrices, we generate SU2. As mentioned before, if we allow complex coefficients, we generate SL2C. So what we will do now in forming the complex coefficients is actually that we will be talking about SL2C. It is a fact that is perhaps not pointed out too much. Okay, so what we'll do, so maybe I should ask first if there are questions to this. If there are no questions, then I go on and explore the representations of the Lorentz group. So first we will explore the trivial representation. So we will call this the 0, 0 representation because we take both n plus and n minus to be 0. Well, if the generator n plus is 0 and the generator n minus is 0, then when we exponentiate 0, we get just 0. So recall that this is a representation of the group. It's, however, a trivial representation gives us nothing interesting. It's a scalar representation, but it is a representation, and it's the lowest representation. So let's start from there. Then we come to the first interesting representation of the group, and that is when we take one of the n pluses, or n plus and n minus, to be something, and the other one to be 0. So here we take the n plus to be 0. So that means that we require this linear combination of generators to vanish. From this constraint, we know that this ik prime should be minus li, such that we have 0. And if we take and insert minus li here, so we have another li minus minus, that is plus li over 2, and that should be our 1/2 representation we require. Then we see that this is solved by li being 1/2 sigma I. So we take n minus to be the ordinary spin 1/2 representation, however with complex coefficients, and we take n plus to be 0. And in this way we then get all the boosts and the rotations. So recall that the rotations are then e to minus I, some parameters that are here hiding in theta, 3 of them dot L, and our L, our generator in this case, was sigma over 2. So in this representation, our rotation is given by this expression. Similarly, for the boost, we take e to minus I eta dot k prime, and the k prime has another I, so the I times the minus I, that gives us a plus, so we have e to eta sigma over 2. Note, not Hermitian generator, or not Hermitian, better say actually not a unitary, because it's not e to I Hermitian. Okay, so for example, we can explore rotation around the x-axis, yes, x-axis, and this would then be e to I some theta, and then sigma 1 over 2. And we have seen it before in the SE2 lecture that it would be this matrix here, axis angle parametrization. This is of course a 2 by 2 matrix, and it is acting on a 2-component object. So the object we call chi, and we call it chi-L as in left. So chi-L then consists of 2 components, and it transforms with this rotation matrix, and generally with these boost and rotation matrices. And important thing to notice here is that in this representation we have this factor of a half here. So this means that we have to rotate 4 pi before we get back to the starting point. And this is an inherent property of the representation of the Lorentz group, that we can have such a representation. So that was the 1/2 0 representation. We also have a sister representation, the 0 1/2 representation. Here we do essentially the same thing, just the opposite. So we put ni plus to the ordinary spin 1/2 representation, and ni minus to 0. Doing that, we derive actually in a few steps that we have actually the same expression for rotation. So e to minus I theta dot L. So same. So the rotations act in the same way on the left and the right chiral representation. However, for the boost, we will acquire an additional minus sign. So compared to what we had before, there is a minus sign there for the right Carroll representation by exactly the same steps as before. And quite generically, the left and the right Carroll spinners, these two component spinners, are called Weyl spinners. And now let's first see if there are questions so far. So now I will go to the van der Waden notation of this. And this is something that I like quite a bit, because it's a much more elegant way of describing the relevant degrees of freedom that we have in particle physics. Unfortunately, it is, although it's very old, it's not explored, and it's sort of forgotten, and it's having a revival right now and in the past decade or two. The fact that particle physics and quantum field theory can be simplified a lot, really a lot, compared to what you will see in Peskin and Schrader and pretty much any standard textbook on quantum field theory that's more than a decade old, or at least 2 decades old. And the simplification is a principle brought about by what we have seen, that is the split of the Lorentz group into these 2 components. So the left, and the so-called left and the right Carroll spinners, and of course this is related to the left and the right Carroll part of the Dirac spinner in particle physics. So let's get to that. I hope to get there before the end of the lecture. And this van der Waden notation, yes, it really is also a notation, but it's a very convenient notation. But at first glance, it may appear strange. But let's now have a look at it. So we have the left Carroll spinner, and we call it chi with an upper dotted index for some not yet explained reason. The right Carroll spinner, we call it chi with some lower undotted index. One could say that it makes sense to distinguish them because they are different. And one way of distinguishing them would be to have a dot on top of one of them and not a dot on top of the other one. Then we also define the complex conjugated versions of these fields, and we define it in such a way that if I take this left guy and the one with the upper dotted index, and I complex conjugate it, I remove the dot on the A. So far that does not make so much sense, but it will make sense. Then I take similarly the right Carroll field and I complex conjugate it, and I add a dot on the A. So if I complex conjugate, I add or remove dots on my indices, but I do not change the upper or lower position of the indices. However, upper and lower indices can be traded for each other with the use of the Levi-Civita tensor and its inverse. So epsilon with 2 upper dotted indices, or epsilon with 2 upper undotted indices, is this. This is just the matrix representation of the Levi-Civita tensor, having 1 here for the 1-2 order and -1 here for the 2-1 order. The inverse of it must have the -1 sitting there instead, and the inverse is then also the guy with 2 lower indices, either dotted or undotted. So now we will connect these different fields by introducing the concept of charge conjugation. So we will see that they are not entirely unrelated. And we define the charge conjugated field as being epsilon times the complex conjugated field. So chi L C is epsilon chi L star. And now we will explore what happens to this guy if we do a boost. So we take this guy and we want to boost it so it gets to itself primed. So the boosted chi, but then we obtained from this guy boosted, so it's epsilon times this guy boosted, and that guy boosted is it's the chi prime, so the boosted chi, and then complex conjugated. So now I consider a boost of my chi L. So this is the boost on my chi L, and I take then the complex conjugate. What I do then is that I insert minus epsilon times epsilon. Minus epsilon is the inverse of epsilon. It's also the difference between these two. So minus epsilon times epsilon is then 1. So I have inserted a 1 here. Then I group this epsilon with the chi and the star. So I have this thing here from over here. I group this minus epsilon with the rest here. So I have then epsilon, the exponent, and the minus epsilon from here. And I should not forget to complex conjugate. Complex conjugating, I have to recall that sigma can be complex, sigma 2 is complex, so I write the sigma star there. Then, to get any further, I use that epsilon sigma I star minus epsilon is actually sigma I. So this you can convince yourself about. It's also related to the representation being pseudo-real, but if you don't have to care about that, you can just do the matrix multiplication for the components 1, 2, and 3. It's not hard, and you should see that you will find this relation. That now, if we look at this expression, we want to get here for the 0th order term in the eta, so we just have 1 and 1, so that would be okay. Then for the next term, we have an epsilon from here, we would have a sigma star from there, and we would have a minus epsilon from here. So that would give us then minus sigma I. Then we can expand the exponent, and we will have more powers of sigma star, but between them, say we have sigma star times sigma star, we can insert more epsilons. So or more ones of the form minus 1 times epsilon. Doing that, we can again use this identity. So for each power of sigma star, we can insert epsilons in such a way that we obtain this identity. In this way, we can translate this expression to that expression here. So we then get e to minus 1/2 eta dot sigma chi LC. So now if we take a look at this expression, what we have found actually is that the charge conjugated field of the left Carroll spinner, with charge conjugation defined in this way, actually obtains a minus sign in the exponent here. And this means that it is transforming exactly like the right Carroll field. So chi LC transforms as a right Carroll spinner under boosts. Then we explore how it transforms under rotations, and we see that what is really changing essentially is that we have an additional I that we have to carry around, and that will turn out to give an additional sign such that we get back the minus sign that we started with. But actually then, so we have the same transformation as for the left field without conjugation, but again we have something that coincides with the transformation of the right Carroll field. So we conclude that this guy transforms as a right chiral field, meaning that it is a right chiral field. So Charlie conjugating the left chiral spinor, I get a right chiral field. Okay, and also since complex conjugation adds or removes a dot from an index, and since we see that epsilon chi L star is chi L, we find that the action of epsilon AB must be to raise an index. So to raise or lower an index. So epsilon chi L, well, I have here my upper dotted index. So if I act with it, it should be with something with matching index position. So I must put this in the lower place. So it should be my epsilon lower beta dot contracted here, and then an alpha dot. So we see that so in other words, the action of the epsilon is epsilon with the dotted or undotted indices, lower upper indices, is to raise or lower the index. So in this way, epsilon acts as a metric. So it is in fact called the spinor metric. For reasons soon to be explained, I'm not a big fan of that word, but it exists, so it's nice if you have heard it. Okay, now what we want to do is something quite important. We want to construct the Lorentz invariant quantities, because when we're considering scattering processes in particle physics, of course, we want something Lorentz invariant. We want to describe nature in terms of Lorentz invariant quantities. And to explore the concept of Lorentz invariance, we must figure out how lower dotted and upper undotted indices transform. So the type of indices that we didn't have before. Okay. So first we recall that the left chiral field that was chi alpha upper dot should go to some chi alpha upper dot prime with this form of the Lorentz transformation. So I had, in this case, I had a minus for the rotations, and I had a plus and no I for the boosts, and the index structure here does matter. So this guy should be upper, and then must be contracted with a lower index here, and I should recover an upper index. So I must have an upper index here, and of course this upper index must also match that upper index, where this is only the beta dots are of course only summation indices. Okay, so this we know. But then we want to derive the transformation of an upper undotted index, and dots were removed by complex conjugation. So I'm considering then the complex conjugated version of this. So I take my chi alpha dot and I complex conjugate it, and I should then have something without the dot. And now I should transform it to some chi a prime. So I take this field transformed here, and I complex conjugate it, because this is how I remove the dots of my index. Okay, so I then take this transformation from here, and this field from here, and I complex conjugate it. Complex conjugating the field removes the dot, so this is what I get. But I should also complex conjugate this matrix here. Now, doing that, the I becomes minus I, so I get a plus sign here. I must complex conjugate the sigma, so I get sigma star. And here as well, I get sigma star. So I have this transformation relation for this field, upper undotted index. And by identical steps, I can find how my lower undotted index, how my lower dotted index transforms. So I have my lower undotted index here. I know how it transforms. It was the right Carroll field. Now I complex conjugate this equation, and by steps identical to up here, I receive this transformation rule. And now, when we know both how dotted lower and upper indices Lorentz transform, we know that this guy is invariant. We want to prove, and we will prove that this guy is actually one of the Lorentz invariants. So let's then consider how this thing Lorentz transforms. So I transform both my fields, I give them prime. And I now collect pieces from up here. So I should have the transformation rule first of a lower undotted index. So it is lower dotted. It is from here. The transformation of the upper dotted index, that was just the left Carroll representation. So this was one of the starting transformations, and so this is standing here. Then I have, of course, a number of summation indices. So this thing here with the pre-index alpha dot corresponds to this guy, Lorentz transformed. This is just matrix multiplication with the pre-index alpha dot there, and then a c dot and the c there. Here it is the same tricks, matrix acting on the vector, dummy summation index there, and free index, free if I consider only this expression there. Okay, now to simplify this, what I do is that I take the transpose of this. So I take the transpose of it, and then I take the opposite component. So instead of taking the alpha dot beta component, I take the beta dot alpha dot component, keeping upper lower position of the indices here. Okay, so I want to transpose this. So I then transpose all the matrices. That will work by just expansion of the Taylor series of this guy. You can transpose the component, the generators, that should do the work. Now, transposing this matrix, which is already complex conjugated, I get, of course, the dagger of it. And similarly here, I get the dagger of it. To this piece, nothing happens. It just stands here. It's copy-pasted. Now, I use that my sigma dagger is actually nothing but my sigma. So all that happens here is that the daggers are removed. So I get this expression here. And now if you stare at this expression here in the middle, you see that we everywhere have the opposite sign, but otherwise the same expression. So for the rotations, we have a plus sign there and minus sign. For the boosts, we have minus sign there and plus sign there. So this matrix is actually the inverse of that matrix. So this gives us nothing but a diagonal matrix if you want to view it as a matrix, or delta b dot c dot. So in other words, I can equate that index label and that index label. So I have chi beta dot chi upper beta dot. And of course, beta dot is just the dummy summation index, which I can relabel to alpha dot, and then I am back where I started. So this thing is equal to this thing. So this is a Lorentz invariant quantity. And in the same way, one can combine upper undotted an upper undotted index with a lower undotted index to obtain something that is Lorentz invariant. So To construct Lorentz invariant quantities, we always need expressions of this type. A undotted index contracted with undotted index, or dotted index contracted with dotted index. Now, this can be formulated differently. So we must combine the complex conjugate of a right Carroll spinner with left Carroll spinner, because if I complex conjugated it, I didn't change the position, but I added or removed a dot. And now we have seen that doing that, we get something that is Lorentz invariant. So I can take this guy, complex conjugated, and also if I want to see it as a matrix transpose, so I have a lying vector here and the standing vector here. So of course them being equal to the complex conjugate transpose and then this guy. Or if we want to write it in component form, the transpose is then irrelevant because we're using the index summation here. So we can write it like this. So now we have come back to this Lorentz invariant form. So we have seen that this thing here is then also Lorentz invariant. So if I take the dagger of the right Carroll field and contract it with the left Carroll field, then I get something Lorentz invariant. Similarly, if I take the dagger of the left Carroll field and contract it with the right Carroll field unit vectors, then I get something Lorentz invariant. Or unit indices, I have this contraction here or that contraction here. So I could construct Lorentz invariants by using one left and one right Carroll field and taking the dagger of one of them. But in addition, actually, I can construct Lorentz invariant by epsilon itself and having two equal types of fields, so two left Carroll fields or two right Carroll fields, and then I contract them with epsilon. So we test the effect of lowering or raising the indices. So I can actually also construct a Lorentz invariant like this. And now, if you look at this, it looks fairly similar to this, which you recognize from the contractional space-time vectors with ordinary Minkowski metric. So you can see that actually the epsilon here plays the same role as the eta here. So this is another reason for calling this the spinor metric. So indeed it acts a lot as like a metric, but I want to point out one thing, a sense in which it is really not a metric. And that is that the epsilon tensor being invariant corresponds to the determinant being invariant. It is not any scalar product that is invariant. There is no such invariant scalar product for SL2C. So instead, for SL2C, the only invariant is the epsilon tensor, which is related to the determinant. So it is not so strange that it is, well, you can at least view it as it is the epsilon tensor that is used to construct invariant quantities also in particle physics and QFT. But frankly, if you say that to your lecturer in QFT, he's quite likely to be lost because this is a fact that people are not aware of generally. Okay. Also, to connect this to particle physics, we can collect what we have learned from the left and the right Carroll fields. So we have learned how the Lorentz transform. We have written it in a few different ways, with lambdas, with indices, or written out. We have written out what the transformations actually look like. It is common, but perhaps confusing to third-year students, that we write this as we write this this object, which is a matrix, as lambda alpha dot beta dot. Of course, this would normally denote the component, but so it's some sort of mixed and not quite consistent notation. But I write it anyway because it appears everywhere, and it's actually at the same level as writing a form active p mu is equal to e comma vector p. It's the same inconsistency with a p mu and then having no mu on the other side. But in both cases, the notation is used because it says something about the transformation property, so there's a point to it. Okay, so anyway, if we don't want to be inconsistent with indices, we can write it like this. We can write the Lorentz transformation of the left Carroll fields like that, and the Lorentz transformation of the right Carroll fields like that. And then if we combine these two fields, and we put first the left field and then the right field, so we put say, the left field in the upper two components and the right field in the lower two components, or vice versa. In any case, we have a block diagonal matrix here, having zeros in the off diagonal 2 by 2 blocks and only having something on the diagonal, implying that this guy and this guy, they do not mix under Lorentz transformations. And this is the beauty of the Weyl/chiral representation in particle physics. So in the Weyl or chiral representation, which I think by far is the most elegant one and the one that should be used, they do not change. The left and the right chiral components do not change do not mix under Lorentz transformations. If one would take the direct representation, they do, and it would be a big, messy 4 by 4 matrix. Possibly I should remark that I here, as opposed to in the particle physics course, I put the left guy upstairs and the right guy downstairs instead of vice versa. So this is the more common convention. Unfortunately, course book in the particle physics course, Kane has the opposite convention. So in that course, I'm following the book by Kane. Now, unfortunately, we have very little time remaining when we get to the real interesting stuff. And this will be a bit of a derivation, so I don't think it makes sense to stop in the middle of the derivation, so I will not start it. But what we will then do instead next time is that we will consider an object having two indices, and we'll do a little bit of calculation, and we will find that we can translate that object having two indices, one dotted and one undotted, into something which is a 4-vector. So we will recover the 4-vector transformation. But I don't think it makes sense to stop in the middle of the derivation. So I will instead finish up now. Tomorrow we will have the exercise class, and I hope that you will be able to present. I hope, so the intention was that the groups should collaborate and make a plan for who should present what exercise. We have no means of forcing you to do so, but it is a good learning experience actually to present something, and I personally believe that the world will just continue to be a bit more digital than it used to be, so it will be certainly more useful than it used to be able to present the material digitally. So I think you should see it as a training occasion as well. Take the chance to do that, and hopefully you learn something from it. And certainly we will all learn, including myself, from the presentation. So what works technically and what does not work so well. Okay, so let's see if we have any questions before we finish off this material. So if not, I'll see you in the exercise sessions and for lectures next week, and we will then continue with the Lorentz group. Maybe definitely go to the Poincare group, to the classification of Lie algebras. We should come as well, and depending on time, we may or may not have so much about Young triples. Okay, so thanks, and let's see if there are more questions in a smaller context.
Goodbye.
I think I may have spotted a small typo.
That could well be.
On page 86, under the in addition, for Minkowski matrix, you have mu and nu for x and y.
Oh, yeah, that you mean
Yeah.
You mean here? Yes, that's a typo. Absolutely.
Yeah.
Actually, this morning there was the same typo here, and so I just corrected it, but I didn't spot it up here. Yeah, thanks.
Yeah, it was just a small typo, so I didn't want to interrupt the lecture for it, but just for
Okay.
completeness.
Yeah, but thanks for pointing it out. I will fix it. It's very useful actually if you point these things out, because I think some students think it's obvious and they don't say anything, and others are confused. And I mean, if we have 20 pairs of eyes staring at the material, they will see things that I don't see on my own, like this one. So thanks for that.
Hej, ursäkta.
Ja.
Vi är i den här gruppen som skulle redovisa problem 2, 3 och 4.
Ja.
Vi har en liten fråga om den sista uppgiften. För vi är lite,
Nu ska vi se. Jag kommer
oklart hur vi ska tyda den.
Vilken som är den sista uppgiften? Vad frågas efter den sista uppgiften?
Det är det här när man ska argumentera att den här Casimir-operatorn, att man kan relatera den till self-energy.
Ja, just det, ja. Det är okej.
För vi som håller på med den, vi har inte läst någon partikelfysik.
Nej, det blir svårare då, jag medger det. Så det är en balans mellan att ha lösbara problem och att presentera intressanta fakta. Men då tycker jag att det är utmärkt att du frågar, för jag förstår att det inte är lätt, men ritar det.
Jag ska säga mitt
Och poängen är då att det sitter ett T i J här och ett, om vi kallar den, och vi säger att den har färgindex I. Här har vi färgindex J och här har vi färgindex K. Så har vi då i det här vertexet ett TA i J och i det här vertexet ett TA. Det är samma A, för det är samma gluon som fäster där och där. Och det är samma J också, men nu är J inkommande, så då sitter J där. Och K är utgående där. Så vi får den här färgstrukturen.
Men är då liksom själva tolkningen i att den här Casimir-operatorn blir ju diagonal om man skriver ut den liksom? Är det bara det då liksom, för att då har du ju
ja, Casimir-operatorn
TI som bara matar till TI liksom.
Ja, precis. Den blir diagonal och här summerar vi över J. Och det blir också samma sak som man gör i uppgiften. Den kallas där lambda I, men lambda I och TA är ju proportionella. Så där har vi ju uppgiften, har vi då kollat på lambda I. Så kan vi ta med några matriser, eller låt mig kalla den lambda istället. Så lambda I, lambda A, den som matrisen I, J, lambda A, J, K. Samma J där och där. Det kommer ju därifrån då. Så, och det här blir ju då delta första index I och K. Så att den här, för att den här ska vara, om man ser det som en matris, så ska det vara proportionellt mot enhetsmatrisen. Så det här kommer egentligen svaret. Så vilken uppgift var det? Var det 3:an eller 4:an du undrade om?
Det var bara 4:an.
Ja, var det delproblem 4 på 4:an?
Ja, alltså delproblem 4 på 4:an. Ja, sorry. Ja, nej, men då var det bara det. Men det här då att Casimir-operatorn, alltså att det är en 3x3-matris.
Ja.
Att man ska tolka det, är det någonting, alltså har det då att göra med att QCD har 3 olika färger eller det har kanske det, jag vet inte.
Ja, det har att göra med det. Så de här kvarkarna kan man tänka sig att de har en färg som brukar kallas röd, grön eller blå, men vi kan också kalla dem 1, 2 eller 3.
Så liksom den här self-energy, alltså är det då att den liksom sänder ut en glon av en färg och absorberar samma och sen nästa index är den andra färgen och så vidare. Okej.
Det är att den skickar ut den här glonen och absorberar den igen, och eftersom det är samma glon så får vi samma A-index här och här, och eftersom det är samma mellanliggande index här så dyker det upp både där och där. Och då kan vi relatera det till uppgiften där man ser att C kommer att bli proportionell. Man finner det explicit om man räknar ut att den blir proportionell mot enhetsmatrisen. Om man vet att den är en invariant så vet man på grund av Cauchy's lemma att den måste vara proportionell mot enhetsmatrisen.
Ja, exakt. Men då låter det som att vi har tillräckligt mycket att utgå från, så får vi se hur det blir imorgon. Ja.
Men bra, så då kan jag alltså räkna med att någon har fixat uppgift 4 imorgon.
Ja, det kan du nog räkna med.
Har ni, just det var 2, 3 och 4 ni hade för 1:an är så lång. Har ni löst de andra också?
Ja, exakt. Det var bara den sista som vi undrar över lite.
Ja, jag vet. Jag tänkte på det när jag formulerade problemet, att det inte var lätt för de som inte har läst partikelfysik. Men jag hoppades att det skulle finnas någon i gruppen som hade läst partikelfysik.
Ja, det finns det säkert, men de har inte gjort sin röst hörd i så fall. Så.
Ja, okej. Okay.
Ja. Men tack så mycket för hjälpen. Så.
Ja, det är inga problem. Ja. Jag tycker det är mycket bättre att ni frågar och kommer vidare än att det inte finns någon lösning imorgon.
Yes, ja men perfekt. Hej!
Hej! Då undrar jag om det finns, do we have any more questions? Jag antar att det är svenska kvar här. Men nu var det kanske slut på frågorna. Då säger jag tack för idag. Okej då.